recording to kick in. Okay, so beams and columns. Similarly, we've been studying so far what we've been doing. It's part of the beams and columns analysis or engineering design. The first part we looked into after we finished trusses. The first part we started looking into was the bending moment diagram, which is the first step into analyzing beams. We have to bending moment diagram and shear force diagrams will give us the maximum shear force along the beam and the maximum bending moment in the beam. That's very important information for us to know, because that will tell us what we are designing against. What's the maximum effect or action on our beam. So the second part, which is a general understanding, which is we will learn it and learn the formulas for it, but this will not be, just keep in mind, this won't be the final design procedure for designing beams. This is a general engineering mechanics procedure for designing beams. Okay, we'll set the basis for what we'll be learning next semester, which is I'm sure that you went through it with Mike, the bending stress in a beam, the formula for bending stress. We agreed that the bending stress is a combined type of stress. It's not a simple stress, combined of two normal stresses, compression and tension stresses. So if I have a beam that's bending around this area, that's developing a tension stress on the top half of the beam, or the top part. I wouldn't want to say the half. It depends on the geometry of the section here. But generally speaking, the top part of the beam will be under tension if we have a hugging kind of bending, and compression stresses on the bottom half of that, or the bottom part of the cross section. Does this make sense, guys? This concept here, that the bending stress is a combined stress, combined of two different stresses. Each one of those, we call them normal stresses. Normal stresses, that means they are normal to the surface they apply to, perpendicular to that surface. We have tension stress on the top part and compression stress at the bottom part. And the formula for the flexural or bending stress equals to M, the maximum moment, or the moment at that point. So if I'm looking for the bending stress on this area of the beam, I'll take the moment at that area of the beam. But if I'm looking at the maximum bending stress, I'll have to go and find the maximum bending moment, and that's what we just learned to do from the bending moment diagram. So it's equals to the maximum bending moment multiplied by y. Y is any vertical distance along the cross section away from the neutral axis. In other words, if I take a cross section of this beam here, if I take a cross section there, and I'm looking at the cross section of the beam, the axis XX here, what you can see it marked as XX, that's where you have zero stresses, and we call it the neutral axis. Why? Because at the top we had compression, the bottom, sorry, let's make it the same as this. The top we had tension, the bottom we had compression. At the center here, the compression will start being reduced all the way to be zero, and then start developing in the other direction as tension stresses, going all the way to the maximum stress here. You can see the maximum tension here at the surface and the maximum compression at the bottom surface. At the point halfway through between these two surfaces, the stresses will be equal to zero. So as a general rule for the bending stress, if I need to calculate the bending stress for any spot or particles of steel, for example, for the steel beam, any particles of steel within this cross section, I can apply this formula and look at the distance between this particle and the neutral axis, which is y. the value y here. Okay. Now, if I need to find the maximum bending stress, where shall I take that? Guys, anyone would be able to tell me if I need to find the maximum bending stress in this cross section? What shall I take the value of y? Did you guys do those during stress strain and properties of material lecture? When we talked about stress strain, guys, can you hear me?
Yes.
Okay, I'm more than happy to know that even if you did them but you forgot them, just please let me know. I'm more than happy to remind you of those. I'm asking, just generally speaking, did you learn this formula before? The bending stress.
No, just the moment of inertia.
Sorry, can you say it again, Stella?
We didn't learn the maximum bending stress formula before.
Okay, okay. Okay, did you learn axial compression and tension stresses, which is always the force divided by the area, by the area, multiplied by the area?
Yeah, is the second moment of inertia are you talking about?
No, I'm talking about axial tension and compression stresses. So if I will tell you I've got a steel rod 10 millimeter diameter and I'm applying a force of 100 kilonewton, how much the stress in this rod? Would you be able to calculate that?
Yes, it's force divided by area.
Okay, that's good. Okay, so generally speaking, guys, all kind of stresses, that's generally speaking, all kind of stresses, sorry, yep, I was reading a quick email. So all kind of stresses are defined in this form. Sigma equals to the force divided by area, okay? Now it depends on the type of the force and usually the direction of this force that will define the type of stress you're talking about. So if I'm talking about tension stress, let's make it that would be tension force. That would be rather than F. If you'd like, we can call it T, tension force. And if you'd like the compression stress, rather than tension force, would be compression force divided by the area. So just to give you an understanding, so you understand what's going on here, when we're talking about 32 MPa concrete, when I'm just saying I'm using 32 MPa concrete, that's what you hear from people, what strength of concrete you're using. They simply 32 MPa, they got a block of concrete, usually it's circular in cross section, always better to test for circular one, and they compressed it onto a certain force. They found the maximum force they applied divided by the area of that cylinder of concrete, and they got the number 32 MPa, which is Newton per millimeter square. So they found the force in Newton, force in newtons, and the area in millimeter square, and the maximum force they could apply before this broke divided by the area. So it depends what cylinder they use for testing. Usually we go by 100 millimeter, 150 millimeter diameter cylinder. So the diameter we usually use by 100 or 150. We compress it by certain force, and if they got to a 32, that's looking at Newton per millimeter square MPa. That's how they specify the strength of that concrete from using this formula of compressive stresses or compressive forces stresses or compression stress, or we can call it the maximum strength of material in compression. Why? Because concrete is famous about being strong in compression. That's what we use it for anyway. We don't use it in tension, correct? We don't make cables of concrete. Instead, we make cables of steel. And therefore, if I need to test a sample of steel to know the exact strength of that steel, for example, you hear 500 MBA steel or 450 MBA steel. How they got that number? They get a piece of steel here. They apply tension forces on both ends. So they fix one end and they apply the tension force into the other end, T. And they look at the cross section, usually the same thing. They use a round section. Why are we using round section, guys? Look at it. Round section, if the force is assumed to be applied in the center, will distribute equally in all directions. So all the particles will work equally. If I use a square section, that means if I apply the force here, the force will take longer to reach here, but shorter to reach these distances. So that's why we usually try to go as much as we can with round cross section to keep the stresses distributed in the cross section uniformly, what we call it. So for steel, we don't compress steel. What we do, we apply tension forces on steel. We get a small piece of that material. We apply tension forces into that material, and the minute this steel will start yielding. So we get, for steel, we get slightly two different values. We get the yielding, I need that. We get the yielding stress, we call it FSY. That's the yield stress of steel. That point, yielding stress, if I draw the cross section here, the relationship between stress and strain, that point is this, after the linear relationship between force and deformation or stress and strain is finished. In other words, within this area here, if I apply the force, then if I take the force, the piece of steel will go back to normal, as if nothing happened. The same as you catch me a piece of rubber. You pull on it, the minute you leave it, it goes back to normal. That's elastic behavior, we call it. That's why we call this part here is the elastic part. And that's where we get the E value, the modulus of elasticity, which is the stress divided by strain. That's a quick review of that lecture, guys, okay? This point here, FSY, that's the yielding point. Anyone will be able to tell me, even it would be great if you remember, even if you don't remember, what do you think is the yielding point? What happens? Why are we calling this point here yielding points? Any suggestions? I don't want you to memorize this, guys. I want you to understand them. See, I'm not memorizing any of this. I'm just talking about it.
After that point, if you compress or apply a tension in the material, you won't come back to the initial form, shape.
Perfect. That's correct, 100%. Thanks for that, Fabio. Simply, guys, the point when we say material has yielded, that means the material gave up. You won. It's a battle between you and the material. If you keep pushing the material, the material has nothing to do other than just give up. That's the point where the material will give up. Okay? In other words, we'll start let go. You're applying the force, the material is still deforming, but will deform without going back to normal. So that will be irreversible deformation. Everything within this area here is reversible, and therefore that's what we use. That's the area we as engineers, we design in. That's why we limit everything for our designs to remain this area here. Unless in some other cases we design there, but that's special type of designs, you don't have to worry about it now. The standard design for most of the engineering work we do is within this area here. Okay? That's what we need to know. because after this point, simply the material will give up. The material will start just going into permanent deformation. We don't want to get there. So imagine that there's a beam, you apply the load on it. After the load is going, that beam stays sagging or bent. That's not a great design, correct? So that's the yielding point. After that yielding point, here, after that yielding point, this relationship is not linear anymore. This part here is linear. As you can see, it's a line in a slope, which is the elastic modulus. But after that point, our relationship is not linear anymore. By the way, this is a simplified form. That point actually is somewhere around here, or in other words, this portion here stopped being linear before that point, but that's not important to you to know now. But for anyone who is wondering about this, there's this is a simplified form of this curve. Okay, there's what we call it non-linear proportion here in this area, but that's regardless, not very important. At this point here, you can see with minimum force we're adding or minimum stress, too much deformation. Look, my line, instead of going up, it's more going to the side. That means I apply a small amount of force and I get too much deformation. That's where we start getting the plastic form. And here, at this point of time, really, again, there is so many different scenarios may happen. It depends on the type of material. It could be just what we call a strain hardening. The material start gaining some extra strength there. It's fake strength, but assumed to be what we call a strain hardening. The material start resisting as much as it can, or may fail from here at this point straight away, or might just go like this. But regardless, in both cases, all of this area here will reach FU, what we call it, which is the maximum ultimate. U refers for ultimate. FU is the ultimate stress this material can reach. So we've got the yielding point where the material will keep resisting and going back to normal. You've got this point, the ultimate point. After this point, simply this piece of steel will just fracture there. Okay, will be cut in half. That's the ultimate where the material will completely fail. Obviously, all this part here is plastic part. Okay, this part here is elastic part. This not used for our design. This is our safe design zone. That's why we always take the yielding stress of steel. So when I'm saying, let's go back here. When I'm saying the yield strength or the yield stress, so stress or strength is the same. So why? Because the yield stress is the maximum, or the yield strength, sorry, is the maximum stress the material can take and go back to normal. That's why we call it strength. So if I say the yield stress for steel is 5 MPa, that means I can apply a force on a certain area. The force here in Newton, the area in millimeter square. If I divide by this by that, that will give me 500 Newton per millimeter square, which is MPa. So that will be a huge force comparing to a small area, because I've got the ratio between them 500. So this is just generally speaking. These two, we call them normal stresses. Why normal? Because look at them, either compression or tension. They are, if I draw this from the side, this is the sample, and this is the force, either compression or tension. Look at it, it's at 90 degrees to the surface. They are normal to the surface. Normal, that means perpendicular. Okay? We call these two are two types of normal stresses. Fabio, you've got a question there.
Yes, just a quick one. So for engineering, elastic material is the one that you deform and it comes back to the shape. And plastic is just the one that you can deform, but
Yes.
it doesn't come back to the original shape. Yes.
That's correct.
Okay.
So plastic material is just plastic. Think about a piece of plastic. If you bend a piece of plastic, okay, what will happen for that piece of plastic if you bend it hard? Will stay as you bent it, right? It doesn't go back to normal. But if you elastic, it's like rubber. Think of a piece of rubber. If you pull that piece of rubber, try to pull it to extend it, you leave it, it goes back to normal. Okay? So we're talking about, by the way, here, we are exaggerating the understanding, but we are talking about very minor deformation. We don't talk about huge deformation there. Okay? These should be part of, did you guys, so just so we'll be on the same page, did you cover those before? Please, if you don't mind me asking this, because I need to know if you guys went through this. Did you?
No, not really, Aaron. I really don't remember.
But yeah, we went, I think.
Yeah, we have studied this with Mike.
Okay, that's okay. That's fine. And I understand if Hannah said that he forgot because something new, you may just forget it. So this is the lecture about the properties of material. How long we've been talking about all these extra forces. This may come, all these forces, when we look at the beam or a truss, all these numbers that we've been seeing, guys, these external numbers are coming from nature. Usually coming from wind or gravity, weight of people, weight of cars, the physical force from person applying that force on a member. So it's all coming from nature, okay? We have nothing to do with these forces. We have nothing to do with these numbers. All what we need to learn, that's next semester, how to quantify them, how to come up with this number. But now we learned, after we have these numbers, how to work with them, how we change this number to a moment, shear forces, reactions. We learned this, right? On a truss or a beam, that's what we've been doing. Next semester, we'll learn how to come up with this number, but there's a missing part there. We have to understand here, even if I work out this number, even if I know how much moment and shear, what else? What's next? I need to know what material. That's the missing part. That's the answer to all these questions. I need to know what material I need to use to resist these forces. And this is the part, what we call it, the properties of materials. So we have to start think about the strength of concrete, strength of steel. What does it mean 500 MPa, 450 MPa, 32, 40 MPa, all of these numbers. Just, I want you to get better understanding. As we agreed, we're not going to memorize anything. Let's understand it. So again, it's always about the battle between the forces by nature, and that's what you, as an engineer, designing. And your job always to win this battle. Nature will apply these forces, the wind, gravity, all of those, and you have to design the material to be stronger than the nature forces. So just looking at lots of these values, that's where we go through the centroid, the moment of inertia. That's not the part I need to look into. That's the stress and strain. So a good example of elastic material is rubber. If you try to pull on a piece of rubber, the minute you let go, that will go back to normal. That's a very good example of elastic material, okay? And the normal stresses, we agreed always the stress is force by area. We talk here about the units. I'm not going to talk about this. I think I had some videos, that's why I wanted you, okay. So normal stresses, let's watch some videos here. What's that connect? Oh, that's interesting. There we go. Sorry. Guys, can you hear the video clearly, or
Yeah,
start?
we're clear now.
Okay, let's try this. Let's start from the start. Anyway. Can you hear, guys, clearly?
Not really.
Not really. Okay. How about this? I'll send you the link. I'll send you the link so you can watch it on your computer. Or I'll send you this later on so you can watch it again. But let's watch the video now, and I'll talk rather than he's talking. Oh, I don't want to go through the advertisement again. That's good. Okay. So let's mute this. See what this is all about. So this is the relationship, guys, between stress and strain, and that's a sample of steel under testing. Okay, I told you we usually take a round cross section, and they are testing this material here. As they are applying the force, there's a tension force being applied here. Deformation, this piece of steel being extended, that's deformation. So we'll take the ratio of the force divided by the area, that will be our stress, and strain is the amount of deformation divided by the initial length of that sample. That's what we refer to as strain. So we plot these two against each other. We find there's a linear relationship between them at the start, and that's the elastic part. That's where the elastic part is finished. That's the linear relationship. After that point there, that will start going into plastic. Look at the steel. It's going into a permanent deformation. That's not elastic anymore. If I stop the force here, this is not going to go back to normal. It will stay like this. And that's what we call it, the nicking of steel. See, there's a nick being produced here, which is the cross section start getting smaller. Nicking of steel, and then that will cause at the end failure. Okay, so these are the values that we need to understand. If you that will take it now in a slow motion. The stress is force divided by area, Newton by meter square, or Newton per millimeter square will give us MBA, and strain is the change of length divided by the actual or original length. So look at it. Let's just go back here. If you look at it in slow motion, you see that's the elastic part. You see the deformation on the steel. Can you see this red sign here showing you how much deformation? That's all within the elastic part. That's where the elastic part is finished. And we hit the yielding point. After this point, the steel, that's it, gave up. Doesn't give you any strength anymore. That's what we call it, the yield strength. If we stop, the steel will go back to normal. Okay, look at it. As soon as we took the force off, the steel will go back to normal. That's obviously exaggerated. Okay, real life is not that much. That's our yielding point. And that's our maximum ultimate strength. After this point, what happens? The steel will start doing that nicking. The cross section will start being smaller. And all of this, it's all within all of that part here, guys, is plastic deformation. It's not elastic anymore. This doesn't go back to normal. And that will cause at the end for the failure or fracture, or steel we call it, okay? I'll send you those later on, guys, so you can watch them. But this is what we do for steel. This is what we do for concrete, for example. Hopefully there's no more advertisement. No, okay. So this is what we do for concrete. It's the opposite. Rather than we do tension, because steel, anyway, concrete is not used for tension. It's used mainly for compression. So we take a sample, we make that sample sitting in a testing jig, and we compress. We add our force here is compressive forces rather than tension forces. And by calculating that force and calculating the cross-section area of that cylinder, that will give us the stress, which is force by area. So these numbers here, it's in American units, bound, so don't stress too much about them, but it's this is general principle. If we measure the maximum force here, what we get from there divided by the cross-section area, by the time this will fail, you'll see in a minute. Let's start failing. And the force stop recording here because there's no resistance anymore. And that will give us the maximum stress this type of concrete can take, for example. Okay? So that's compressive stress, which is again the same thing. These two, if you noticed, all the forces applied perpendicular, look at the forces, are perpendicular to the surface, at 90 degrees to the surface. That's why we call these forces normal stresses. Both of them, tension or compression, both are normal. Whereas the bending stress is a combined stress between the two of them. The combined stress containing, if you look at this shape here, when I'm bending a member, look at these lines. This is pure bending. Look at these lines, they're coming very close to each other here. They're separated at the bottom. That means this is combining two different stresses. These are being compressed and this side here being under tension. That's why we call this type of stress as combined stress between the compression and tension together. Okay? That's what we call a flexural or bending stress. And the same as any other stress, guys. Look, it looks like a rubber. So very elastic material. If I push too hard, if this wasn't a rubber, let's assume it's steel, and if I push too hard down here, I'll go through the elastic stage, which is after I take the force, this will go back to normal. But there's a point where I reach a yielding stress, either in tension or compression, or in bending, which will cause the steel to be permanently bent, so it won't go back to normal. So the same as any other stress will go through the elastic phase, then the yielding point, then we go into plastic phase. Okay? This is a combined stress made of two normal stresses. Now the one slightly different stress, we call it the shear stress, which is again the same exact thing. It's force by area, but this time the force not perpendicular. So you remember the first two things we talked about, normal stresses, about the first two normal stresses, the force were 90 degrees on the, check if I have that, the forces were 90 degrees on the surface. In shear stress, the force is parallel to the surface. So we'll look at that. I forgot what's in these videos, to be honest. There we go, that's shear stress. Look at that, how the shear stress, it doesn't try, look at this, shear stress, it doesn't try to compress the bolt, or it doesn't try to tension the bolt. What it tries to do, just move half of the bolt this way, the other half the other way. So laterally, let's call it. Or the force, if I draw the force here, the force will be this way here and that way there, pushing the port. If you look at these forces, both are parallel to the cross section of the port. If this is the cross section, the forces are parallel to this cross section. So this is a shear stress, not a normal stress anymore. Anyone has a question, guys? I can hear some microphone.
Yes, me.
Yeah, go ahead, please.
Aaron, just a general question. Like, generally speaking, we put steel inside the concrete to make stronger when we talk about tension. Is there anything that we can add to the concrete to make stronger about compression, or no, just the concrete by itself it's enough? Like, generally speaking, of course, like you don't need to be like deeper into any case.
So simply, when you say concrete, that's Paolo, right? I can't see the names who's talking, but
Fabio.
That's Paolo. Fabio. Okay, thanks, Fabio. Sorry, I'm trying to recognize your voices, guys, but I'm working on it. So, Fabio, when we say the word concrete, concrete is not one thing. It's a mix of materials: cement, water, aggregate, sand, all of this. To make concrete stronger, you can just make that mix ratio is different to start with, which is you can use more cement, which is the cement is the bonding agent, less water, but you have to mix them thoroughly, and maybe smaller aggregates. Okay, so that will create stronger concrete to start with. So concrete, you have 25, 20 MPa, 32, 40, 50, up to 100, up to 130, you name it, type of actual concrete. That's one. Two, there is some additives we can add to concrete, additional. So when you talk about concrete, guys, think of concrete as a chemical reaction. Concrete is not a material. It's just you're putting different materials together and you're creating chemical reaction, and that is the outcome of this chemical reaction. So the slower the chemical reaction, the more you can give it time, the stronger it is. That's one. Two, it depends on the ratios of this material going into that chemical reaction that will determine your strength. Thirdly, you can add other additives, what we call them, or compounds into the actual chemical reaction that will form the atomic bond between these chemical material in a slightly different way. We create stronger bond there between them. Okay, so you can create stronger concrete. That's chemically speaking. Now, physically speaking, we've done different testing on adding some fiber or glass fibers or carbon fibers, small pieces of those into the concrete mix, to see how these fibers may try to bond the concrete particles together, and that adds some strength, not too much. We added, instead of fibers there, the carbon or aramid or glass fibers, we add some steel fibers, very small, fine steel fibers, not steel reinforcement. We cut small pieces of steel and we add them to the mix. And these bits of steel, they just simply work inside the concrete to connect and bond all the concrete together. So there are some other materials, but there's really concrete itself. Just to answer you, Fabio, there, concrete itself, it never been an issue to increase the compressive strength of that. There are lots of options to do that. Okay, mainly it's creating the balance between concrete and steel, and sometimes confining the concrete is the bigger challenge. Confining it, that means keeping it within that shape. So we usually add some mold on the outside, either carbon fiber, glass fiber, or steel, all of those. We talk about this in more details, guys. Please, let's try to keep it as concise as possible here. So just going back to this shear stresses, did that answer your question quickly, Fabio?
Yes.
Okay.
Thank you.
No worries. So shear stresses, guys, as we said, the main thing, the first main difference is the direction of the force. Not normal to the surface, it's parallel to the surface. So you see now, let's have a quick look at that. What does that mean? If I have a joint like this, guys, if I have two plates connected with bolts, this plate is trying to move this way, the blue one trying to move to the right, the yellow one trying to move to the left, because that's why we're connecting these two plates. They're trying to separate, and the bolt is keeping them together. So what these two plates are doing, applying forces here on the port parallel to the cross section of the port. So these type of forces are shear forces. Look at them. These are the forces trying to shear the port. And that's what happens when the port will shear. The same thing here. If we have three different plates, that means we have two different shear plane between them. There. So I'm just talking about, for example, this joint here. If I have this joint by a port, that joint will create on these two planes here, that we call them shear planes. That's where the shear forces will accumulate. That's where the two pieces of steel trying to separate, and the port is keeping them together. So by adding the force, regardless, that's just trying to show the calculations. The point here I want to try to make, that if you look at the force here, let's take a simplified example with one shear plane only. If I go back to this arrangement here, on this port here, guys, on the left-hand side, let's say the force applied here is 500 newtons. The cross-section of the port, let's assume it's 100 millimeters square, for example. Okay, so I've got 500 divided by 100, that would be 5 MPa. Again, it's force divided by area. The shear force this time, it's not normal force, divided by cross-section area of the port. So long story short, guys, if we go back to here, don't know why I have another one here on shear. Yeah, it's just the same thing, just another experiment, how we test the shear of bolts. They're applying force upward, and these forces is held by these bolts, and you'll notice shear failure is a sudden failure. You'll notice here you will notice in a minute that the failure will happen just suddenly. Okay, so shear failure, keep in mind, is the most dangerous failure we may have on a structure, because it doesn't give you any warning, it just happens. Okay, comparing to bending is more predictable. Okay, so that is enough for reviewing previous material. That will give us enough information to what we need to discuss in today's lecture. Let's go back to our today's lecture, talking about bending stress again. So, bending stress is made of two different forms of stresses. These two forms of stresses are tension and compression stresses. These two different stresses are normal stresses. Each one of them has its own way to be calculated. But now to calculate the bending stress, we have a slightly different formula. We call it the flexural stress or bending stress equals to M, which is the maximum moment or the moment at that cross section, multiplied by Y. Y is the distance for any of these steel particles away from the neutral axis where tension and compression are zero. If I go back to that video, look at this. I've got compression here at the top, maximum compression, tension at the bottom. Somewhere here in the center, the tension and compression are equal to each other, and they counteract each other because they're both equal in value and opposite in direction. He is trying to push into the section. He is trying to pull away from the section. So if I take a screenshot of this, go back to our whiteboard. Bending stress here, guys, if I draw that, the shape of bending stress on this cross section, here the forces are trying to pull away because it's tension until I get to 0. And here the forces are trying to push until it goes to 0. You see, that's the shape of bending stress, normal shape of bending stress. Maximum at the two ends and 0 in the neutral axis of the beam. Make sense? Just generally speaking, if I ask you which one is most along this cross section, for example, which part of this cross section is most stressed under compression? You say this particular point here is most stressed under compression. Or let's not look at that cross section, let's look at the center cross section, this one here. This point here is the maximum point stressed under compression. And this point here is the maximum point stressed under tension. So the maximum compression stress or bending stress, which is a combination of these two, the maximum compression stress is at the top, the maximum tension stress at the bottom, or I can say the maximum bending stress is at the other end of this beam, top or bottom. They are equally to each other but opposite in direction. So maximum the flexural stress. Close that old lecture. Flexural stress here, FB, we're referring to it, which is really generic name. M multiplied by Y divided by I, IXX, moment of inertia, or IYY, doesn't matter. M is the moment around this point. Moment, I can get it from bending moment diagram. I got point load here, that means the bending moment diagram is like this. If I draw this beam, simplify it, point load in the center, that means the bending moment diagram is like that. Because the shear force diagram, if you remember, it is like this, and bending moment diagram would be like that. And I've got the maximum value of that bending moment is M here, this one. Y now, the value of Y, I can look at it, I can calculate the bending stress, not just only at the top, I can calculate it at any point, maybe here, or there, or there, doesn't matter. Any point along the beam, I can calculate that bending stress. If I am looking for the maximum bending stress, I should know that I have to calculate it the top or the bottom, which is the extreme Y value. Look at it. Y is that. We call it then, that Y we start calling it C rather than Y. Make sense, guys, that Y value?
Yes.
Okay, anyone please didn't understand that Y value thing? Can you please turn on your microphone because I can't see comments here. Anyone did not understand that? Please let me know. All what we're saying, yes? Someone would like to say something?
Yeah. I don't get that letter C there. That is, you said that is C because of the compression?
Yes, yeah, that's correct. Please do not mix between these two C's, okay? This is compression. I was saying this is compression forces. So let's call it CF. Someone turned the camera by mistake, Paolo. You've got your camera turned on. If you just let you know, mate, it's up to you. Okay, so we've got the let's call this CF and TF, so we can make sure that we differentiate. This is just a similar name by coincidence. That has nothing to do with it. This is the compression forces, tension forces, top and bottom. But all what we're saying, I can calculate the stress, the flexural stress in a beam at any point within that beam. First of all, to start with, at any section, I can calculate here, there, and there, and there. Wherever you choose that section, all what you have to do, use the value of M for that section. Let's call it M1, 2, M3, 4, 5. Doesn't matter what you choose, because each one of those has it. Look at it. M1 here, 2, 3, 4, wherever. Each one of those will have.
Sorry. So your bending moment diagram is, I think, the opposite side.
What do you mean the opposite, Ina?
The,
Are you saying it's going like this, top rather than bottom?
so
is that
the
what
biggest moment part is the up, not a bottom.
Yeah. So what you're saying, Ina, you are saying bending moment diagram should be like this, right?
Yes.
Which is the same. That's what I'm saying. I'm trying to say.
Yeah. Yeah,
What we agreed on today, that bending moment either this way or that way will be the same. I don't want you to get too hung into dice. This is only saying it's bending downward or upward. As an actual value will be the same. As an actual numerical value will be the same.
Yeah.
Why?
The gravity.
Yeah, okay. Why I draw it this way, Ina, because next semester we will agree on a slightly. We use this direction here, so we can come up with the method for shear force diagrams and bending moment diagrams, positive, negative, keeping everything uniform, right? We agreed on everything negative down, positive up. But you will learn in engineering mechanics next semester. We will get over this sign convention for structural analysis only, for structural engineers. That's not for engineering mechanics. That's for structural engineers. What we usually do, we agree on bending moments acting. The bending moment positive is sag and negative is hogging. And usually we draw the positive down and the negative up. That's what we usually do.
Yeah.
Okay, so regardless.
Maybe other students will be a little bit confused, so that's why
Yes, yeah, no, thanks for that, good point. But regardless, guys, let's assume that, okay, let's assume, so I don't confuse you, the bending moment diagram is like that. The maximum bending moment we're trying to say is in the center. Regardless is positive or negative, the maximum actual bending moment will be in the center. If I need the bending stress at one of these locations, I have to take the moment of these locations to start with. And also, it doesn't matter just where I take the moment, and I still have the option where about within this cross section do you want the the bending stress. Do you want to know the maximum bending stress? That means you have to take it on the outside. If you want to take it in the center, that will be equals to 0, because again, the bending stress here will be like this. If you want to take it somewhere around here, we take that point there and we take the value y for that point. Okay? Why do we need this? Because one day when you're designing concrete, for example, you need to know how much the stress in the steel. If there's a steel bar here, let's assume there's a steel bar here. If you need to know how much the stress in the steel, all what you have to do, calculate the stress, bending stress at that point. Okay? Which is M by Y. We need to know how far is this steel from the centroid or the neutral axis of the beam, divided by I. the overall height for the beam. Okay, this is all just for understanding, but for calculations, which is much more simpler, if I ask you what is the bending stress for any beam, sorry, FB equals to My on I. That's the general bending stress at any point within that beam. If I ask what's the maximum bending stress of a beam, that would change. So let's call it FB max equals to, first of all, M max. I'll have to find the maximum bending moment along the entire beam. So I'll go to my bending moment diagram and use this value, the maximum M max. That's one. Two, I have to take the maximum value of Y. So if this is my beam, for example, if I tell you Y is the value from any point here to the neutral axis, what would be your maximum Y? This is your maximum Y, right? Half distance, like half depth of the cross section in theory. So that Y max, or what we call it C, the distance to the centroid. So multiplied by C divided by I value, moment of inertia. Right, guys? Can you just keep in mind this is the maximum bending stress in beam?
Aaron,
Yes.
can I consider that this C would be equals to half of the length, the width of the
The depth of the beam. You can,
depth?
you can, as long as your shape here is symmetric, correct? Which is all the examples we were coming across. This shape will be symmetric up and down, so you can always assume. I don't want to tell you, that's why I'm not saying this as a formula or a rule for you, Paula. All I'm saying here,
Yeah, I
It's-
understand.
mm,
I think in many cases we don't have symmetry. For example, if
Exactly.
we have a short top and a large bottom,
exactly.
but we have in some kind of symmetry, but it can not be applied in some cases because the force is not coming from like axial directions. But I understand what you're talking about.
Yeah, that's 100%. And just to make it more comfortable to you guys, all the examples we'll be looking at will be symmetric shapes. I don't want to go overboard now in terms of finding the centroid, because we learned that from before, from calculating the centroid and the moment of inertia. We can do it, but I'm not going to combine all problems at the same time. Most of the cases that we will be looking at, we'll be looking at symmetric shapes, okay? So this is our formula for maximum bending stress. I've got Rafael, you've got a question?
Yes, Aaron. What's the value of I?
So I is the second moment of area or moment of inertia. There's no one value for I. If we have a rectangular shape like this, and I'm trying to find I for that shape, it would be BH cube on 12. B is the measurement, sorry. B is the measurement parallel to the axis. So if I'm finding, this is XX. If I'm trying to find IXX, B is the value parallel to the XX. That means B, H cubed on 12. H is that value perpendicular to the axis, that's H, and cubed on 12. That's for rectangular shape.
I got confused now, Aaron, because
Mhm.
I think we learned that the second moment of inertia is the moment of inertia, the sum of the moment of inertia plus area multiplied by distance square. So
Yes.
this formula if you use the B H cubic divided by 12, we are assuming the moment of inertia, not the second moment of inertia.
I'm not saying second moment of inertia, I'm saying second moment of area or moment of inertia.
Okay, yes, okay.
Okay, so Ix is second moment of area or moment of inertia. Okay?
Okay, thank you.
All good. So, and we hardly use, by the way, the second moment of inertia. So you don't need to worry about that one, Stella. All what we use is second moment of area or the moment of inertia. Okay? Try to go back and check what we've done in the previous lectures. That should be always the second moment of area or moment of inertia. That's the value we use for structural engineering. Okay, so as a formula, you can memorize this, guys, and please, there are some basic formulas. You need to know them, memorize them. By the way, in your final exam, you're allowed to bring an A4 sheet with formulas of your choice. Obviously, A4 sheet with formulas, reasonable formulas, not to be font size of 5. Okay, just a reasonable amount, font of 12. Cheat sheet, yes. Okay, and trust me if I tell you this, and I'm trying to tell you the right thing for you, the more formulas you put there, the more confused you are in the exam. You don't have too much time in the exam to navigate through formulas. The more that you can memorize these minor formulas, you should memorize them. So the I value, the moment of inertia or second moment of area, is for rectangular shape BH cube and 12. B, please remember, is parallel to the axis that we're looking at. H, perpendicular. So the perpendicular value always cubed. Therefore, if I need to calculate an I section, you can do the parallel force theorem, if you've done that before, or you can simplify this to a series of rectangles. As long as these rectangles, they all have their centroid on the neutral axis. For example, so this is the second moment of area or moment of inertia relationship, BH cube on 12. H is always the perpendicular, B is always the parallel. For example, this is the same as that. If I need to calculate the moment of inertia for this shape, guys, can anyone calculate that for me? How would you do it? Do you remember at all? Can you please, let's turn on the microphones, keep the open discussion. I'm not, as you said, I'm not examining you with what you learned before. We're just trying to think out loud. If I need to calculate the moment of inertia for this shape, what would I do, you reckon? I have two different approaches, either simplifying it to this formula or use the parallel axis theorem. Anyone will have a...
It's gonna be 150 times 210.
Okay.
Cube.
Okay.
Divide 12.
Okay.
Yes, this is the moment.
Okay. So let's look at that and see what Hannah suggested for us. This is the shape we're trying to work with. What Hannah's suggesting, I'm calculating XX, assuming this is X here. Ixx equals to BH cubed on 12. That's what Hannah's suggesting. He took B is the width, 150, which is the parallel, multiplied by 210 cubed on 12. If that's the case, Hannah, how come the moment of inertia for this shape will be equal to, let me draw this shape for you. If I have this all made of steel, what would be the moment of inertia for that? If this all here made of steel, which is much stronger, would be? That would be that formula, what you said there. So I can't say this is the correct answer. Leo.
And if we calculated two rectangles and just like take it off.
So can you explain that?
Yeah, so we're still doing the what you've done before, like D times H squared divided by 12. So we do the same stuff we do those two rectangles. Can we do that?
Which two rectangles?
Yeah, I'm just saying like the 180.
Yep.
Okay, let me check. So that's gonna be, so what I think, I'm not sure if it's right, but what I will do.
Yeah, no, that's what I'm saying. It's just.
All right. So I would use 140 times 180.
140 came from.
Yeah, so 150 less 10.
Minus 10.
Yeah, minus 10. Yeah, that's right. And then times 180 cubed divided by 12.
Okay. Okay.
And then I will take this result and
subtract it.
Yeah, that's right. Yeah, subtract from the first one. That's
Okay,
how I
perfect. Perfect. Okay. Paolo, do you have something to add to this?
Yeah, can you hear me?
Yes.
So you can do as well, you can calculate the 3 moment of area and sum from the 3 rectangles.
So you're saying what 3 rectangles? This one here?
The top part, yeah, the top part, the middle part, and the bottom part, using the same equation. So be 1 divided by 12, then multiplies base times height times base cubed.
Yep.
And you can do this for each of these 3 areas of steel.
So let's say, I can say Ixx.
150 millimeters times
150 by
times 15 because
15,
it's
because 210 minus that would be 30 divided by 215 cubed.
Yeah.
On 12. That's multiplied by 2, I would say, because the same thing for the other one.
Yes.
So multiplied by 2 plus that
Plus the
center
middle
one.
part. Yeah.
Okay. That's the mistake I don't want you guys to make. And thanks very much for that, Paolo. Thanks for just thinking about this. So this is a very common mistake, and that's why I was very clear when I said you can add and subtract things from each other. That's correct. As long as, where is the centroid for this? I'll draw the centroid for what Paolo suggested. That's the first centroid. That's the second centroid here. And that's the third one. These 2 centroids, they don't have these 2 shapes, they don't have their centroid on the neutral axis. I'm taking the moment of inertia for this shape around axis here. So that won't be Ixx anymore. That will be X1, let's call it X1, and X2 here. So that's not Ixx. That's not the moment of inertia around this neutral axis. So let me go back to what Hannah suggested, part of the solution. And I think, was it Leo or?
Yeah, that was Leo.
Okay, Leo suggested the second one, which is accurate enough, but let's divide it and simplify it, guys. What I said, the formula of pH cubed on 12 will apply to any rectangle as long as the centroid of that rectangle on the neutral axis. This is our neutral axis. I'm looking for IXX. As long as the centroid of that rectangle, you choose any rectangle you would like. You can add them and subtract them from each other. You can do anything you want as long as they're centroid in here. So in this particular shape, what I can do, I can take one large rectangle and the centroid of that rectangle is here. That's all, assume it's all made of steel. But in reality, that's not all made of steel. Minus, I can take this rectangle here, let me draw it in a slightly different color, minus this area of air. Look at this rectangle here. And the centroid of this rectangle again here on the neutral axis, minus that too. Okay, so if I say the large rectangle, pH cubed on 12, minus 2 multiplied by pH cubed of these two on 12, that will be correct. So let's call it, this will give me let's choose the other color. The yellow one will give me the large value, let's call it IXX1, and each one of these two will give me IXX2. So my value of IXX equals IXX1 minus 2 multiplied by IXX2. Each one of those are easy calculated. Each one is pH cubed on 12 for each rectangle. Okay? Or you've got too many options. You can take the large one minus, for example, all of this center one, that's all minus, plus I have to add this again. Look at it, the large one minus the red hatched one, that took away the steel part, and then I can add it by itself. All of these rectangles, they have centroid on the neutral axis. That's another way you can do it. And this method will be very easy for all kind of symmetric shapes. For example, if I'm looking at a shape of hollow section, we'll call it rectangular hollow section, a very common shape. This is steel and this is hollow. If I say, guys, I need to ask you this. If I say 100 by 5 SHS, what does that mean? Anyone will be able to tell me?
Square.
And if the engineers...
100 base.
Square for a
Yes, Ina, please go ahead.
square.
Square. What does it mean, 100 by 5?
It's the outside of the same length. So height
That's,
and the
yeah.
and width.
For the depth and the length is 100. What about the 5?
And then the thickness is a 5.
Perfect. So when I'm saying SHS, square hollow section, square hollow section, we need to know these names from now on, like you know your friends' names. These will be your new friends, guys. For example, UB. Anyone will tell me what UB is if I say
Universal beam.
perfect. UB refers to universal beams. UC,
Universal column.
perfect. What about 100 by 50 by 3 RHS?
Rectangular.
Is
Rectangular hollow section. Please, let's say the proper names for those, okay? Rectangular hollow section. What about if I say 180 PFC? Silence.
So,
I'm sure, thanks to Thiago mentioning, I'm sure Nathan did mention those to you guys. PFC, let me make it
hi.
simpler.
Something with column.
Parallel flange something.
Okay, that's good. Leo, parallel flange channel.
Yeah, that's right.
These two parts here, we call them flanges. This is flange. This is flange. So the top and the bottom part are flanges. The vertical part we call it whip. This is whip. Okay? So parallel, both are parallel to each other. Flange, channel. The shape is channel. And the two flanges are parallel to each other. PFC. RHS, rectangular hollow section. That means the cross section. That means the cross section is rectangular, not square. This is square. This is rectangular, hollow, empty from the inside section. The highest number is the depth, second number is the width, and then the thickness. Okay, we've got the square hollow section is the outer measurement, and the thickness are the important part for us because it's square. What about if I say 100 by 5 CHS rather than SHS?
Circular hollow section.
Perfect. Circular hollow section. So I'm looking at a circle with the thickness of 5. 100 is the diameter, okay? Outer diameter. Okay, so we went off topic here, but these are important things that you need to know. And you can take it either way. First of all, as assurance for you that you will learn all of those before you leave, or as something may worry you, because I can guarantee none of you guys will leave my classes without knowing those inside out, okay? We have to be very good at those. So if I am looking at this cross section, as I said, the square hollow section, let's keep those back. If I need to calculate the moment of inertia for a square hollow section or rectangular hollow section, for example, I can use the same exact method. Look at it. I can take the outer rectangle, which is the centroid here, minus the inner rectangle, which is the centroid here. So this is a very easy, useful method for calculating IXX for values, or IYY. IYY if I'm calculating the other way around. Okay, so let's go back to our lecture. Delete all of this. We just reviewed what we should have known, how to calculate the IX for a section. So if I need to calculate IX for this member, I'll take the larger one, which is 150 by 210 cubed on 12 minus, I'll take 2 of these rectangles, minus 2 multiplied by, each one of these rectangles, that width there is 150 minus 10, 140 divided by 2 is 70. Okay, that's 70 millimeters because 150 minus 10, that's 140 divided by 2, 70 by 180. 70 by 180 cubed on 12. Done. That's very simple calculations you can do. So equals to 150 multiplied by 210 cubed on 12 plus, sorry, not plus, minus 2 multiplied by 70 by 180 cubed on 12. That will give us, I can't move this one. Please don't close. Close. Did you remember the number at all? That's gone. Would be 447 something. I can't. No.
47722.
Oh, I need to know how many decimal digits. That's okay. I'll recalculate it. Just when I click on this calculator with my digital pen will close. Okay, 150 multiplied by 210 to the power of 3 of minus 2 multiplied by 70 multiplied by 183 on 12. So I've got 1, 2, 3, 4, 5, 6, 4, 7.7 times 10 to the power of 6. That's how we usually write it, guys. So you get familiar. What's the unit here, guys? Do you reckon? Anyone will be able to tell me the unit for the moment of inertia?
Millimeter over 4.
Perfect. Thanks for that, Stella. Look at it. Millimeter multiplied by millimeter cubed, that will be millimeter to the power of 4. And these are the values you see in your tables. Like if you look at your tables here for the steel sections, need to go structure analysis, book, steel. These are the catalog, product catalog, or the information or the capacity tables, what we call them, for different type of steel beams. So if I rotate this shape, look at this shape, it looks weird and square and awkward. We call it welded beams. It's simply made of plates, we weld them together. You don't see round edges. You don't see radius here. They are square. Why? Because they are made of series of plates welded together. We call them welded beams. The same thing, but different arrangement. We call them welded columns, which is shorter, but thicker and wider. We call them welded columns. And then we move on to the universal beams. They are more round because they are hot rolled, we call them. These type of sections, guys, we call them hot rolled steel. That means they heat the steel until it's malleable, will melt, roughly will melt, not liquid, but malleable, what we call it. You can bend it easily, and they form them into these shapes. We call them hot rolled sections because it's very thick steel. You can't bend the steel when it's cold. You have to heat it up. This is the universal beam. So the IX value, and just let me go through these shapes further. Universal columns, the tapered flange beams. Look at the flange here. It's not parallel anymore. It's tapered. Gets smaller, tapered. Called tapered flange beam. Parallel flange channel. the two flanges are parallel to each other, guys, are slightly different. That's the UCs. We have the tapered flange channel. I'll see if we have it on this catalog. If we don't, I'll find it somewhere else. So we have a different type of channel. The two channels, the two flanges here, they are not parallel 100% to each other. They are tapered. They get smaller here. We call them tapered flange channel. That's universal bearing bars, which is similar to the universal beams. Equal angles. They are just angle, equal in both sides. So if I say 100 by 5 EA, that means 100 millimeter in each side, and the thickness is 5. EA equal angle. Unequal angle. Now that's again the equal angles. Unequal angles, which is the same, but one of the edges is longer than the other. Call it unequal angle. So if I say 100 by 70 or 100 by 80, UEA or UA, sometimes we call it. That's the one there. By the thickness, that means unequal angle. So this you might see UA or UEA. Both are common. Unequal angle. They are very easy when you get used to them. Very widely used. So they are really easy to memorize. All these letters based on the shape, simply. We've got rails sections. That's not for structural, mainly for rails, obviously. So if I go back to any of these sections, for example, the universal beams, one of the values we find there, IX. IX refers to the moment of inertia around XX axis. That's XX, and that's YY. So we have two moments of inertia around the strong axis and around the weak axis. What we call X is the strong, Y is the weak. Why? Because if you calculate the moment of inertia around X, you'll find it much larger than the moment of inertia around Y axis. Look at it. For any section, moment of inertia around X is much higher than the moment of inertia around Y. It's more than 30 times roughly here. It's more than 20 times, kind of, okay? What else? That's the format. When you read this number, it's not only 986 multiplied by 10 to the power of 6 millimeter to the power of 4. That's why I used here. Look at it, 47.7 multiplied by 10 to the power of 6 millimeter to the power of 4. Makes sense, guys?
Yep.
Okay. Yes, Aaron.
Okay, good, good. So if I give you some shapes, you'll be able to calculate the moment of inertia for these shapes, you reckon?
Yes, sir.
Right then, let's see this shape, for example. Let's take this. Can you please all calculate the moment of inertia for this shape? Around XX. I need IXX. Please finish your calculation and type your number into the chat bar. And I would like to see everyone please try in it. I know some of you guys, this could be new information, could be challenging, but please try your best with it, okay? Ina, you're not always wrong. So far, you've been 99% of the times correct. You made some mistakes, I make mistakes. Everyone makes mistakes. That's fine.
Thank you.
Anna, can I please ask you to see if you could try with it? All what you have to do, follow the formulas that we talked about. Do you have anyone with you? Do you have microphone there, Anna? Anna, not Hannah. Anna, please. That's you, Anna. So, do you have microphone there at all? Okay, whatever makes you comfortable, Anna. Just please make sure that you give it some time, okay? I've got large hopes on you, Anna, okay? I'll follow up on this. All right, someone turn on the microphone. Freddie's not happy. What's going on?
I'd say it's all good, man. Just I need to know how you get the middle part, those 15 mm. How to get that part there?
What do you mean how to get that part?
Because I'm trying to get after 2 times, there is -2 times something there. So
yeah. So I think about it, geometry, look at it, Freddie, without complicating things. Can you tell me the area of this triangle here?
That will be...
You need the depth of it. We have it, 200, correct? Yeah. But what about the width? Think about it from all of this info. How can you get that?
Okay, we have 150 in the top there.
Yeah.
So I suppose that is the half?
That's 150 all the way from here to there, correct?
Yeah, so that will be 75.
But that... But don't you, to find this gap, you have to take this, all of this is steel. You don't want to take 150, subtract that from it first, correct? Which is 150 minus 15. That's 15 here, correct? Okay, Freddie, what we're trying to find is this distance here, correct?
Yep.
This distance equals to 150.
Yes.
Minus this distance divided by 2.
Okay.
Yes or no?
Yeah, well, I need to see it actually, but...
Look, it's just, think about it this way. Think about it this way. You ran for 150 meters.
Mm-hmm.
But you had a break in the center for 15 meters. You stopped.
Mm-hmm.
So if I tell you I ran for 150 meters, but I had a break in the middle for 15 meters.
So that will be 60. 60 each side.
Right? Because,
yep.
Hold on a second, before we just... All I said, I ran 150 meters and I had a break for 15 meters. How much did I run to start with?
Well, you were running 150 or that is 75, and then you take 15.
Why 75? So I'm saying that the overall distance, sorry, put it this way. I crossed an overall distance of 150.
Yep.
Most of it was running. Most of this distance was running. But in the center, I walked for 15 meters only.
Yes.
So think about it. If I go from my home to Tonsley, I had to cross 150. This 150 meters within that 150 meters, I had to walk for 15 meters only. How much did I run from that 150?
90.
Which is 150 minus 15. So this is my home.
Mhm.
This is campus. This is 150 from here to there. In the middle here, I walked, this is walking, 15 meters only. I crossed overall from my home. So I left home, I start running. Then I had a break, walking only for 15 meters. Then I continue running. How much the running overall is the distance minus the walking distance, right?
Yep.
So 150 minus 15. So overall, I ran 135 meters.
Mm-hmm.
Combining this part and that part. And if I tell you these two parts are equal to each other, that means each time I ran 135 divided by 2.
Okay.
Which would be something. So I've got there
7.5.
Exactly, 67.5, okay?
Okay. Okay, so sorry, just basically those 15 meters or whatever the millimeters are just the distance between
That's
yeah,
the thickness of the steel
yeah,
there.
the thickness of yeah, exactly. Okay. Yep. Thank you.
No worries. Okay. So got some values from everyone. Let's just do it quickly here. We agreed the Ix value for this, Ixx equals to BH cubed on 12. Actually, I'll just, rather than putting formulas, will confuse you, I'll just put it as numbers. Ix x equals to, the first B is 150 by 225 cubed on 12 minus 2. I'll do it in a slightly different way. Learn how to write straight on this screen. We'll do it in a slightly different way. Let's try this. Ixx equals to 150 minus, sorry, multiplied by 225 cubed on 12. I'll do it now in a slightly different way, minus this overall, if you'd like. Check this one, Freddie, if it's easier for you. So the large shape minus all of this shape, all of this together, which is minus, what do we have there? 200, not 200, sorry, 150. 150 multiplied by 200 cubed on 12, plus I have to add this again, plus, which is 15 by 200 cubed on 12. Let's try this and see if you guys got the same number. That's another way you can calculate it. So 150 multiplied by 225 power of 3 divided by 12 minus 150 times 200 to the power of 3 divided by 12 plus 15 multiplied by 200. Is that what you guys got? So 52, 1, 2, 3, 4, 5, 6, 53, 52.4 times 10 to the power of 6 millimeter to the power of 4. Roughly about that. Okay, 3, 8 or 4. All good? So this is another way. See, so please, just doesn't take longer to calculate Ix. Is very simple, very, very easy thing. Just get your head around it, practice it. How to practice it? Put as many shapes as you would like, as long as they are symmetric shapes and try to find your values around it. What about if I ask you to calculate for this section here?
Aaron,
Yes.
can you show how to calculate PFC, please?
PFC is a parallel axis theorem.
Oh, sorry, equal angles. Sorry, equal angles.
The same thing, parallel axis theorem.
Yeah, okay.
Okay, so you have to use parallel axis theorem.
Okay, that's it.
All good. So, what I was going to say, I was going to draw this. Do you guys have problems with the parallel axis theorem? Do you want to go over that? I don't have time for it, to be honest. And I'm sure Mike did cover it. He told me specifically that he did cover it properly. Do we have any major problems with that?
I'll just try to remember because there's a lot of time, but I'll study by myself.
Okay, just have a look at it. If you have questions, please let me know, okay? I'm not really too hang on that. I'm not really too worried about that one, about calculating moment of inertia for non-symmetric shapes, because usually we have those. And in real life, if we have one of these cases, we use software to calculate them, okay? But at least for a standard shape like this, you should be able to perform that at least. So, yeah. Anyway, can I ask you, can anyone calculate IYY for me here? Rather than IXX. Do you remember definition of BH cube on 12? We said B is the value that it's always parallel to the axis. H is the value is always perpendicular to the axis. So can anyone calculate for this shape IYY rather than IXX? Please. Anyone? Guys, it's the same exact principle. All what we said here. Can you have a quick look with me, please? All what we'll be looking at now, B will be H and H will be B. But I have to look for rectangles again, the same. All of them, they have to be on the YY axis. So if I look at this rectangle, in other words, let me simplify it for you. How about this? In other words, all we have to do, how can I do this? I have to, in other words, all I have to do is that. This is your section name. Simple as that. And your YY is just here. So I can take the overall, rectangle minus, now I can't take these two, by the way. Can I take minus this, minus that? And if I can't, can anyone tell me why I can't? Well done, Jiang. Why can't I take these two?
Because they don't have the same center of mass.
Perfect. The centroid of this is here, the centroid of that is there. They're not on the axis that I'm looking for. What I should do instead, I have to take, as we agreed, the larger shape. Minus this shape. Look at these two shapes. They have the same centroid on the axis. plus this shape. Okay, but now this is my B and this is my H. Simple as that. So my I, Y value, but without even like, that's good. You can, let's take, that's good. You can think about it this way, but without even rotating it, you should be able just looking at it normally. I can't. Yep, okay. You should be able to just look at it this way. All you have to do in your head or your mind, just making sure that your H now is that way and your B is that way. So my II value, the larger one, B is 225. 225 multiplied by H is 150 cubed divided by 12 minus this large rectangle here, which is the height of it is 150 and the width is 200, so 200 multiplied by 150 cubed divided by 12, plus I have to add this one again, which is again, the width is 220, the width is 200 again, multiplied by 15 cubed, divided by 12. If I calculate this, multiplied by 150 cubed divided by 12 minus 200 by 150 cubed 12 plus by 15 . Is that what you got? And one guy's calculated that 70. Yep, perfect. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So 7.08 times 10 to the power of 6 millimeter power 4. Okay, guys. Why we got some slightly different numbers from Jian and Leo and Stella. Can you please, did you find where you made the mistake? Or did we make a mistake here, do you reckon? What did you guys do? Jian? Guys, Janet, can you?
Yeah, I calculated. Yes.
Yeah.
Now I followed your equation and I got the same number. But previously, calculated. When I calculated, I moved the center beam to the edge of the larger rectangle. So I make large rectangle and then just take over the smaller rectangle.
So you took the large one minus these two?
Yes.
And we agreed?
Just assuming that you move the center beam to the either edge, to the left or right.
Can't. No, we can't. We can't. You see, moment of inertia is area multiplied by distance. So the minute you start changing the location of that area, you're changing the distance from the centroid. Okay, so we can't do that.
Okay.
So it has to be Has to be accurate, okay? So that means, guys, I'm trying just to read between the lines here. I think you need to do some more practice on calculating moments of inertia. And I'm checking. Have you done these examples? Most of them are parallel axis theorem, but have you done them?
Yes.
One of them, yeah.
Just looking for the important part for me, if I can find some symmetric shapes that you can practice your. I'll send you some shapes, guys, that you can practice just calculating your moments of inertia, please, around X and Y. Okay, let's be familiar with that, because definitely this is needed in the exam. Okay. There's no symmetric shapes here, that's fine. Okay, so assuming that we know how to calculate moments of inertia, which is, please go back and practice that. I'll give you some examples that you can just, I'll send you some examples that you can practice those, please, okay? Simply look for any I section, look for any hollow section, look for any, mainly these are the two sections that we deal with in structural engineering. If you notice, most of the beams are this shape or just a pure rectangle or a hollow rectangle or square. Okay, just at least practice these shapes. That will definitely be needed in the exam. Okay, so assuming we calculate the I value, that means all what we have to do calculate. For calculating the bending stress, let's go back. Calculate the bending stress for a beam. We have to find M, maximum moment, multiplied by C, which is the maximum distance from the neutral axis. In our case here, for example, it's 225 divided by 2. In the previous example, is 210 divided by 2. It's always the maximum distance from the neutral axis. That's C. The moment value, we get it from the beam analysis, from looking at the entire beam together. Get the bending moment diagram, we'll find the maximum moment, that will be our moment value, and divided by Ix, X or Iy, depends on how the beam is bending. We'll talk about this more. Most of beams, guys, if you notice, Ix is the highest. If you ask yourself before, that's why most of beams are placed in this position. You hardly see a beam placed like this. We never use a beam like this. Not never, we do in some cases for different use, but we hardly use a beam like that, carrying load from here. Always, or most of the time, we use the beam carrying load from there. Why? Because the beam is deeper in that direction, and the Ix value is much higher than Iy value. This is the I value from Iy from this direction. So if I go back to this example, can you please try to solve this for me? Calculate the maximum bending stress in the beam shown below. What do you need to do to calculate the maximum bending stress? This is our FB max equals to M multiplied by C divided by I. What is the first step I need to do, guys?
Reaction.
The diagram.
Moment. Diagram.
So reactions, moment, all of them correct. So the first thing first is reactions, and then we have to find maximum moment. Can you please find the bending moment diagram or the maximum moment? It's up to you. the only one way to find it is to draw the bending moment diagram. Can you please do that? And give me the maximum moment on this beam, please?
Aaron,
Yes, mate.
do we have the IXX of this beam?
This is your cross section.
Oh, sorry. Yeah. Do we have it? Because we already calculated this one.
Yes, you already calculated. Would you mind calculating again, just to double check?
Okay. Now, yeah, because I already found the other values.
Yep. It's just for practice. That's all. Because then I need you guys.
Okay. I'll do it again. Okay, no
Thank you.
worries.
So I'll start with the solution along you guys. Sigma MD equals to 0. That will be 10 by 2 minus 6 by 6. minus plus. See down. 26. And we've got 3 by 26, that'll be 60, 78, and 24, 48. Straight negative going down by 30, and positive going up by 78. And I've got already 30, there'll be 48 up. So M max 48 kilonewton meter. Okay. You guys, anyone will agree with this number? I've got the maximum bending moment 48 kilonewton meter. I'll calculate the IX value equals to, we agreed, so 210 cubed by 150 on 12 minus 2 times. I've got, what do we have there? 180 cubed by 150, take 10, 140 divided by 70 on 12. So we have 210 power 3 by 150 minus 2 times 70 times 80 power 3 12. 1, 2, 3, 1, 2, 3, 47.7. 6 millimeter power 4. FP max equals M. Now, keep in mind, guys, this is 48 kilonewton meter. Can I have everyone's attention, please, into this one step, please? What we calculated from here, kilonewton per meter. So I can rewrite this to keep all my units uniform. If I need to change this to Newton millimeter, so this I have to multiply it by 10 to the power of 3 to be newtons, and this is by 1000 again to be millimeters. So it'll be 48 times 10 to the power of 6 millimeter, sorry, Newton millimeter. 10 to the power of 6, that's 6, okay? So my flexural bending stress equals to M 48 times 10 to the power of 6 multiplied by Y, which is half of 210, so it would be 105. That's in millimeter, and that's Newton millimeters. All my units are uniform, divided by 47 times 10 to the power of 6.7 here, times 10 to the power of 6. These two would cancel each other, and that will give us 48 times 105 divided 47.7 will be 105.66 MPa. Why is it MPa? Yes, why is it MPa? Because it's always in Newton per millimeter square. In other words, I can write it in Newton per millimeter square. Our answers should be in MPa, guys. Let's keep using the uniform units, okay? In a great job. Just keep an eye on the units, please. So you've got in kilonewton, that means you multiply it by 10 to the power of 3. Meter square to millimeter square, you have to divide by 10 to the power of 6. So that means you divide it by 1000, your answer. All right, guys, does it make sense? Can you please, if you're still writing, I'll wait for you. If you're still doing your solution, I'll wait. If you finish, can you please just say, I'm done, so I want to point out some comments on this, what we've done. Can you please, if you finished, type on the chat part that I'm done, please. Good. Okay, guys, let's try to put more understanding. Actually, I'll wait for a little bit because I've got some people still writing. Where's Mr. Hannah? I didn't hear your name, Mr. Hannah, today.
Really? I'm here.
That's good. That's good. Well, I didn't hear. Yeah. Leah, do you have a question?
Sorry, where did you get this 105?
That 105 there, this 105 here, it's simply 210 divided by 2. Do you remember we agreed C value here, half the depth of the beam, that's C. the formula here we have F equals to M multiplied by C on I. C is half of the depth. If the depth is 210, divided by 2 would be 105.
Oh, yeah, that's right. Thank you.
All good. Okay, guys, let's try to get better understanding why we're doing this headache nonsense so far. Look at it. So far, what I've done here, without applying any safety factors, by the way, we did not talk about any safety here. Without applying any safety factors, but what we've got so far, based on these loads, based on 30 kilonewton could be weight of a machine, 50 kilonewton could be weight of a column supporting another building on top, doesn't matter what they are, all supported on a beam. I came up with a number here in MBA, which is the maximum stress in that beam. In other words, what I came up with, please focus with me. What I came up with, I can say, if I use steel of 105 MBA or stronger, for example, if I use 200 MBA steel for this beam, in this cross section, in this length, and these forces, this beam should be safe. Because I can choose 200 MBA, 300 MBA, 400 MBA steel, doesn't matter. It's different type of steel. This gave us, guys, what's the minimum strength of steel that I need to use to resist these stresses. Make sense? Does it tie all together? So that's your job down the track as an engineer. Just if you 1 second, if you don't mind, Fabio. This is your job, but in a more refined, we will learn more comprehensive and refined formulas in our next semester. But this is the general understanding. Look at this. By knowing the forces, we learned how to calculate the maximum shear and maximum moment. By understanding the strength of material and the property of that cross-section, which is the moment of inertia, as an engineer, you have the knowledge to quantify that. To resist these forces, you have to use, for this cross-section, for a different cross-section, we can come up with different numbers because I value will be different. But for this particular cross-section and these forces, I can use 200 MBA steel and that will be okay. This is down the track will be your advice as an engineer to quantify a size and type of steel to be used for design scenarios. So we have now the bigger picture or the complete picture. We have the loads. From the loads, we learned how to change these loads to a more graphical view for us, which is bending moment diagram and shear force diagram. Now understanding the strength of material, we combine them together to calculate what we call it stress. By knowing the stress, I can compare, do you remember that picture I showed you? It's comparing between the strength of the material, the robot that you're designing, and the nature, what force is throwing at you, which is these forces here. Could be gravity, could be wind, could be anything. You can say, if I use, or you can tell your client, if you use 200 MBA steel for this scenario, you'll be safe. Make sense? We don't have to, perfect. We don't have to overthink it. This is, I don't want you to think, Aaron, is that what we're going to do for every design night? We will do it in a different way, but this is the same principle, the same engineering principle. There's one missing link here, which is, I did mention it, safety. If I tell the client use 105, for example, I say to the client use 106 MBA steel and you'll be safe, I'll be completely wrong because I don't have any safety margins for my design. This is not going to happen. Why is that? Because all these forces here, guys, you'll learn next year are theoretical forces, estimated forces. Can any one of you tell me that you can predict wind? Can any one of you tell me that you can predict how many people will walk in the same room at the same time? No one can predict that. What we do, we use an educated guess based on experiences, statistics, and education. We make our best guess to estimate this 50 kilonewton and 20 or 30 kilonewton. So those may vary. So that's why we have to always keep safety factors, not that only, but also, can anyone of you tell me that when the manufacturer of this steel beam, they made it all 100% accurate with that strength steel all over the beam? There's some areas here where heat, we agreed this would be melted down to be able to be formed to this shape. When they heat it up and then cool it down, these particles of steel, they maintain what we call it residual stresses. They stay too hot on the center here. Think of the particles of steel in here. They stay too hot, but the ones on the outside will cool down. And when they cool down, they form solid material, whereas in the inside here is still not very solid and still hot. When this tries to relax in the center, it can't because everything around it has set already. So this will cause these particles in the center to be pressured or confined. So we call this process residual stresses. So there's lots of other faults in manufacturing could happen. Who tells you the contractor on site will not make mistakes fixing this beam properly? So there are lots of things that may go wrong. That's why always, as important as your accuracy in your work, who told you that you didn't make minor mistake, hopefully, in your calculations? So it's as important as you make your calculations accurate, you have to use safety factors. And safety factors will apply in, generally speaking, in two different forms. We will talk about them now, okay? Do you understand the importance of safety factors, guys? Any questions about that? Fabio.
Yes, I have a question. Like, okay, if we take that point C, and if we look the cross section of the beam, on the top we have compression, and the bottom we have tension, right?
Correct.
So this value that we found, 106, is the same for the top or for the bottom, right?
Yeah, that's for the entire beam. That's for the entire beam.
Okay. Because we got the Cmax, but I got the Cmax positive and the Cmax negative, right?
Yes, that's correct.
Okay, so in the case of the steel, what is more critical, the compression that I'm suffering on the top or the tension that I'm suffering on the bottom? I don't know if, like...
No, that's a very, very, very valid question, and I'll make you answer for yourself. Okay?
Okay.
And that's to everyone, guys. What Fabio is asking, very valid question for steel. Which one is more critical, tension or compression? Think about it this way, Fabio. I'll give you a very small example, which is a steel ruler. Thin, narrow, long steel ruler. Which way do you reckon the ruler will be stronger? If you try, which way do you reckon the ruler will fail quicker? If you try to push down on it, or if you try to tension it? I bet you, if you try to tension it and you call all your friends and your family, and I'll be with you guys, and everyone will try to pull on it, we can't do anything. It's not gonna move. Steel is very strong in tension and very strong in compression too. But the problem comes in place if we all push on it, or if you only push on it, the geometry of steel, it's not very stable because you're creating a thin. That's why I'm saying this is the general principle. Next year we will learn more details. There's a there's the concept of buckling. And we did talk about this buckling concept when we talk about two force members, if you remember. Fabio, if you're saying something, I can't hear you because your microphone on mute. I can see you might be saying something, or could be just noises around you. But if you...
No, I'm just hearing.
Okay. So we talked about this previously when we talk about slender members, and we talked about two force members. We talked about, you saw it when we push on a long, thin member, that member will straight away buckle away, will bend laterally, try to escape the load. So usually steel, because steel is very strong in tension, we don't need to use thick steel. We tend to use, look at those plates, always we tend to use thin plates, but spaced away from each other. That's creating the issue of steel usually will fail more in the compression zone. So when we design, that's what I'm telling you guys, that's what we'll be learning in more details next semester. When I design a steel beam, I'll be always concerned about what we call it, the critical flange. And most of the time, not all the times, critical flange is the compression flange. So these are the two flanges you have there. And I will be always keeping an eye on the critical flange. In most times, compression flange is the critical flange. That flange will tend to bucket, to escape, run away. We'll talk about this later on. Okay? That answer your question, Fabio?
Yes, like now it makes sense.
Okay. So, guys, talking about safety factors, let's go back to that. Are we clear on the importance of safety factor? Do we understand where things may go wrong? You may make a mistake. Type of mistake could be contractor on site not fixing things the way it should be. Loads are not accurately estimated. You've got too many mistakes. That's why always you see it again. I keep saying next semester you will learn this in more details. You see how many safety factors we apply along the way to keep our design safe. So in terms of safety factors, think about it this way, guys. Please focus with me on this one here. When I'm talking about a strength of material to be safe, that means I have to make it stronger than what it is. Make sense? So instead of saying here I need 105 MPa, I should somehow use a safety factor to make this number larger. So strength, we have to make it larger. Make sense? Loads, if I'm talking about using safety factors to apply to loads, I have to make the loads larger too. So always just so you don't get confused. Sorry. Just always think about it logically speaking. When I'm saying apply safety factor of 1.35 for loads, what does that mean? If I'm telling you apply a safety factor of 1.35 safety factor for loads, what does that mean, do you reckon?
You have to increase your 30 and 50 kilonewton force by 1.3.
Exactly. Thank you, Stella. So that means I'm telling you, make your loads 35% larger. Look at them. I multiply 50 by 1.35. That means I made my load 35% larger. Okay? And I made this load 35% larger. So I'm amplifying. I'm making my loads larger. Okay? But if I calculate strength of material, I have to either, in this case scenario, if my client asked me, Aaron, can you please tell me what grade of steel I need to use, but I want a safety factor of 2.5, for example. What shall I do here? So he's asking me what
You can
strength.
just multiply the number that you found
Perfect.
by 2.5 and then find the next one.
Exactly. So the client is asking me, Aaron, what grade of steel shall I use? But I would like to have a safety factor of 2.5, for example. Then what I tell him, your minimum, that's what I tell him. He doesn't know this calculation. He doesn't understand what is this. All what he needs to know, I'll tell him the minimum Fy for steel, you should use equals to 105.66 times 2.5. He doesn't know these numbers. All what he needs to know, 105.66 times 2.5. He needs to know that the minimum you should use is 265 MBA steel. That's what he needs to know. He doesn't need to know about all this headache. Okay? Makes sense where the safety factor comes in place? Or the other way around, if I tell you this beam here is 250 MBA steel, whatever we calculate there, 265 MBA steel. What maximum moment this beam can carry, for example? Or what maximum load, not load, let's say what maximum moment this beam can carry. But use a safety factor of 2.5. Let's take this to the side here.
So now you have to divide.
Yeah.
Exactly. So if I just go back here, where is that beam? This is the first one. If I just came to you and saying, Aaron will be using this beam for our design. Actually, that's a question to all of you. I'm your client, I'm saying, all right, guys, I'm using this beam in one of my buildings. Can you please tell me what is M max? What's the maximum moment I can apply on this beam using safety factor of 2.5? Can anyone give me a number? If you know this, we agreed IX for this beam equals to 47.7, I think it was, times 10 to the power of 6. We'll check that number. Yeah, 47.7. So if I come to you with this inquiry, what would you be able to tell me for a safe moment? What is the safe moment I can apply on this beam? Sorry, I forgot to tell you here. This is using a 250 MBA steel. If the strength of material is 250 MBA steel, this is here, 250 MBA. And I'm asking you, what's the maximum moment I can use or apply on this beam with a safety factor of 2.5? Let's think about it. we agreed the maximum bending stress equals to MC on I. Okay, I need to find M max. But here, don't forget your safety factor. So at this value here, which is 250 MPa, the maximum stress or the maximum strength. So we call this one as a stress. Or strength. Guys, does it make sense why I'm calling this stress or strength? Think about it. Maximum stress, sorry, I'm saying maximum strength, that means this is the maximum stress that steel can take and still okay. So that's how strong it is. That's why we use maximum stress or maximum strength. Make sense? So when we say stress or strength, roughly are the same. It depends how it's been used, by the way, of course. So all I'm saying here, the stress in the material is 250 MPa, but to be able to keep that on the safe side, I have to divide this by 2.5. So I'll put here 250 by 2.5 equals M, which is I need to find, times C value there is 105 divided by 47.7 times 10 to the power of 6. If I calculate from here, M equals to this multiplied by 250 divided by 2.5 multiplied by 105. So M equals to 250 multiplied by 47.7 times 10 to the power of 6 equals divided by 105 multiplied by 2.5. That's the moment. Now that's in Newton millimeters. Look at everything we got there, Newton millimeters MPa. So if I need to make it kilonewton meter, I have to divide it by 10 to the power of 6. That's my answer. 45.4. So I can tell my client the maximum M max you can apply on this beam is 45 point something was 0.4 to kilonewton meter. Okay, or what you could have done, you could have find the value of M and divide the value of M by 2.5. We'll do the same. All good, guys? Hold on a second, 250. Yeah, no, that's right. I used the smaller one. So all I did, I reduced the steel strength by 2.5.
Aaron, can
Yes.
I ask something?
Mm.
Like the safety factor is 2.5.
Yep.
And should we need to increase the 250? Not a divide multiple 2.5.
If you do that, you get a larger value for M, correct?
Yeah. So
And that's not safe.
Oh.
Correct?
Yeah. Yes.
Yeah. So I'm assuming here I'm using weaker steel. All good? So always think about it logically, guys, so you can make your judgment on it. Your value should be on the safer side. Which one is more safe? Have a larger moment or a smaller moment? Okay.
Yeah, that's a problem because when I calculate and analysis the structure, I just put the safety factor not by hand, and then
Yes.
I think I lost my understanding.
That's okay. That's okay. Because anyway, this is again, guys, this is very, very preliminary view on safety factor. I just want you at this point to be aware of safety factors. You will learn next semester that these safety factors, we apply them in different ways. I'll give you an example. So these forces that you got there, 50 and 30, the first thing 50 kilonewton and 30 kilonewton. The first thing we do, we apply factors to make these forces larger. So if it depends what type of forces, that's the understanding we'll learn next year. If these forces are dead load, or in other words, excuse me, if these forces are weight of material, so we have really good, accurate understanding of these forces, we can look at the material and calculate these forces. We multiply just 20%, so we multiply those by 1.2. If these forces, for example, let's say I have, for example, if I tell you that arrangement, we've got 50 kilonewton here, 30 kilonewton there. So I understand what we do next semester, which is you don't have to worry about it now. And I told you these are the weight of the upper floor. So these are point loads of the upper floor, G. We call them G, dead load or G. And I tell you also, this beam is supporting the floor for an office or a house, for example. Let's take a house. A house, that means this will have a uniformly distributed load, UDL, of 1.5 kilonewton per meter. But this is live load, we call it Q. This is G. G, which is weight of material, it's usually estimated accurately because we can look at the material, calculate exactly how much does it weigh. But can anyone predict accurately how many people will be in this room at that same time? We can't. Therefore, the safety factors will be 1.2 multiplied by G plus 1.5 multiplied by Q. So we add 50% for live load, and we add just 20% for dead load. That's what we do in structural design, actual structural design next year. So we have more structured approach on this. And also, when I go to find the capacity or the strength of this beam, I multiply the strength of this beam by 0.9. That means I take just 90%. So this beam can carry 100 kilonewton meter, until my client can carry only 90 kilonewton meter. I take just 90%, I reduce it by 10%, negative 10%, always. So there are different ways we will do this next semester. Not worried about this. Now, all what I need to know now that I'm raising your awareness of safety factors. All good, guys?
Carol, I just confused because if we have a bigger moment, it means we need to change the member size, and then we need
larger member.
Yeah, and then it means it's gonna be more safe.
That's correct, but that wasn't the question. The question the client was asking, Ina.
Yeah.
For this member, I already have. He already have this member. What is the maximum moment can he support? That means I have to give him a smaller moment to the actual moment that this member can support.
Okay.
Okay. So what you could have done, let's do it in a slightly different way if you would like. Let's delete this. We got here 45, correct? Just to make it more simpler. We said the formula we have FB max equals to M by C on I, correct? F, the strength of steel, we have 250 MPa, equals to M, we need to find the value, times C, which is 105, sorry, by 47.7 times 10 to the power of 6. That means M equals to, if I calculate this, (47.7) multiplied by 10 to the power of 6 equals divided by 105 equals, that is, and divided by 2, 3, 4, 5, 6, that's gone. Sorry guys, this calculator is not the best, but it's the best I can show you how to do it in your calculator. Okay, let's do it again. 47.7 times 10 to the power of 6. 10 to the power of 6 divided by 105. Multiply by 250. So that equals to 113, 1, 2, 3, 4, 5, 6, 113.57. Kilonewton meter. Ina, all what I've done here, I didn't use the safety factor. All what I came up with here, I'm saying a beam with this steel strength and this geometry can support 113 kilonewton meter moment. But if I want to design a safe moment, let's call it here safe M equals to 113 divided by 57 divided by 2.5. So 113.57 divided by 2.5, and that equals again 45.42. Make sense?
Yeah.
Now?
No, I got it.
Okay, so it's the same thing. You can, if you want, leave the safety factor. In fact, maybe it's a better way, an easier way for you guys now. Leave the safety factor till the end. Do your calculations properly and apply the safety factor at the end. Okay?
Yep.
And make your judgment there by multiplying or dividing.
Okay.
All good?
Yep.
All good. So, all what we've done today, we didn't go too far. We went just for the beams. And we talked about safety factors. I will put this lecture notes on Learn. Our next lecture, guys, we'll talk about columns. Now, I would like to highlight here, please, to make sure that we go with columns, and columns will have a bit more logical judgment we have to apply there to make sure that we go smoothly there. And that's, I'm asking all of you, please, if anyone doesn't find themselves clear on calculating the I values, please practice this as much as you can. Just how to calculate an I value. IX for symmetric shapes. I'm not asking you for non-symmetric shapes. I'm not asking you to use the parallel axis theorem. Just for symmetric shapes, for the easier ones. Practice this, because our next topic, talking about columns, we have to start looking at calculating IX and IY. They are different. So please, for any shape you look into, we have to look at it. We have to calculate the IX and IY values. All good? And I think I do have some examples for you to practice for beams. Engineering mechanics, see guys. So we've got a few examples. Please practice them properly. And when you see one of these shapes on a side note, please try to calculate IY too, not just IX. You will need IX for this question. That's a neutral axis, XX. But try to practice the IY too, because we need it for columns. Do question 1, 2, and 3, please, and 4 and 5. Question 6 onward, that's columns, but please do the first 5 questions. All good, guys? They are very similar to what we discussed. Have a quick look at the notes, lecture notes that we've got here. Try to read through these safety factors comments. And if you have any questions, please send me something, and let's try to please, before you send me any request, do your part. Like, if you have a question, go ahead straight away, ask me the question. But if you would like me to make a quick session, as you've seen, there's no quick sessions, at least each one of those goes for an hour. Before you ask me for one of those, please do your part of studying the lecture notes and watch this video. I'll stop recording now so we don't make this video longer than what it is.